Today we'll be going over electrical print basics. We'll talk about what is in an electrical prints package. We'll talk about common items on a drawing package, how to navigate an electrical prints package, common electrical components in an industrial automation system, and how common components are connected to a system. The purpose of an electrical prints package is to detail how all of the components are connected together so that the system delivers power and communicates properly. When we integrate an industrial system, it is comprised of many small systems all working together to create the final product. The purpose of the electrical prints package, what we find in the electrical prints package, is information that should detail what devices are connected within those systems, and specifically where every termination, signal, and ground should be landed. The electrical prints package is extremely useful for system installation and system debug. When systems are not providing power or communicating properly, the electrical prints package is the main resource for troubleshooting and diagnosing electrical issues. What we find in an electrical prints package is the title page, which gives the overall description of the project, an index page, which gives the page and sheet number and description of each page inside of the package. We find the title block, which is information about the specific sheet and about the project, the interconnection diagram for each major component of the system, including cables and connections for each major component. We also see internal component layouts for each major component of the system. And this is going to include placement of all the electrical components inside of the major component and the wire layout and routing inside of the major component also. We'll find the internal circuitry for each major component. This will detail out all the connections between the internal components and all connections to all interconnected major components also. You also see a bill of materials, which is a listing of all the parts and components inside of the major component. Usually each major component will have its own BOM, and then we have spare sheets, which serve a purpose in the electrical prints package. Every sheet of an electrical prints package will have a drawing and a sheet number. Every number in the drawing and sheet number has a significance. So as we see here, we have a project number 16, a drawing sheet number 16-0672-120-001. The first six digits of the number are the project number. And what the project number is, it's the base number that ties all of the drawing packages together. So we'll have a 120, a 240, a 570 package that will all have the 160672 base number. In fact, the mechanical and the electrical prints will also have the same base number for each project. The next three digits are the drawing package number, and this is the number that identifies the major component described within. Major components include things like the PDP or the power distribution panel, the SAC or the system control console, the robot controller, the robot itself, items like these. The last three numbers are the sheet number, and they identify the sheet inside of the drawing package number, or for electrical prints, inside of the entire sheet package. Standard automation has specific drawing package number meanings. So for the middle three digits, the drawing package number, there are specific meanings for the first digit and then the last two digits. The first number details what zone the drawing package relates to. Is it a prime zone base, clear coat, sealer, LASD, anti-chip, an installation package, or a cable chart? The last two numbers of the drawing package number dictate what type of device family the drawing package is in. So if it relates to the SAC, it'll have the 10 for the last two digits. If it is a type of a junction box, it'll have a 20 as the last two numbers. And then we have things like PCEs or pneumatic control enclosures as well as controller application packages too. For the 120 that we see in this system, that number would reference a prime code for a number 1 in the first digit, and then a junction box for a 20. So a 120 would be a prime junction box. The title page. We see an example of the title page both on the left and the right of the slide. We see that the title page has the customer logo, the customer name, and the project location at the top. We see that it has the project description clearly labeled at the bottom of the top of the drawing. There is an equipment description, so what exactly is being put in, what major equipment is being upgrade is being done to the system. In this case, it's an R30IB P250IB robot with an integrated 2K Versabell 3. Then we see what engineering package type this is. Electrical drawings for this specific version, but there are also mechanical drawings available. Then we see the engineering company, location and logo, followed by the project number at the bottom of the page. For an index page, the index page looks very much like we see on the left. It's a long list of items that detail out the drawing number, the drawing description, and the sheet number for each of the drawings listed inside of the electrical prints package. And what we can see in the blown out regions in the right is that we have the sheet number in consecutive order, the standard project number, so what drawing package does it relate to, and then we have the drawing title and description in the third column. This is used to quickly navigate the electrical prints package. If you know you're looking for a specific component, then you can quickly navigate to where that major component is and investigate the package for that specific component. In the upper right area, we see that there is controller and standard drawings. These are drawings that are not necessarily project specific. They were generated by either another engineering company or for standard product. We see that the main controller application package for a P250 is included from FANUC for both the P250, the opener, and a supplemental package by Standard Automation for the controller application package. We also see that there's system cable identification chart and a molded cable identification chart available as part of the package. Even on the index print, we see the title block area. On this print specifically, we do have a customer title block region with the information that's requested by the customer for the engineering package. But then we also have the lower portion, which is actually along the right side of the page. That contains a significant amount of information both about the drawing package itself and the overall electrical prints package. The first part of the title block is the sheet information area that we see in the top right. That includes the designer, the engineer, and the approver of the drawing sheet itself. It has the project number and the date that it was created. It also has the file name, the drawing number, and the sheet number, as well as a different orientation of that same information on the left. To the right of the sheet information, we have the package information. This gives the drawing package title, and then below that it gives the sheet title. So the drawing package, the 120, or in this case, the 120 drawing package is what is listed out, as well as the system drawing index. To To the right of the package information, we have the engineering company on file that created the drawings and their contact information. And then we also have revision information to the far right. Revision information is important. It tells you what level and when the latest revisions to that sheet were made. You can judge the age of a drawing and by its revision. You always want to make sure that you're working on or off of the latest revision of the drawing possible. After the index sheet, we have interconnect diagrams. These are used to show how major components connect together. It shows the general layout of all the electrical devices and shows the cable connections between the major components with cable part numbers. It also gives the information for the drawing package for each of the major components. So if we look at the drawing on the right, we can see that we have the power distribution panel, the PDP, the system control console, or the SCC. We can also see that, we can also see that we have encoder information as well as the robot's location relative to the SCC. If we zoom in closely, we can see around the SCC, shown in the bottom left of the slide, that we do have the package number for the SCC, so that would be 16-0672-121. We can also see that the cables that plug into the SCC in this location are called out, as well as how many pins are in each connection. After the interconnect diagrams, we have the internal component layouts, and this shows the layout and the orientation of the smaller components inside of the major component. It shows communication devices, I/O connections, terminal strips, the robot encoder rack. It shows any relays and any other devices included inside of major hardware. We can see that there are dimensions here, as well as terminal strip callouts as additional information to better help with debug and installation. As part of the internal circuitry, the field device tags and tag numbers are shown in the layout. If we zoom in on the top area of the robot of the SCC layout, shown in this diagram, we can see that the device tag for chassis 1 is 3401 ADP. Now, those 3401 ADP designation has meaning. The last two numbers of the device tag number give the line number that the device is found on inside of the electrical prints package. The remaining numbers are the page location. So for a tag 3401, it means that it's on page 34, line 1. Tag 232 would be on line 32, sheet 2, and tag 22334 would be on line 34 of sheet 223. The ADP just means that it's an adapter. Now, looking at sheet 34, line 01 in the electrical prints package shows slot 0 of the chassis 1 adapter. The green line shows the direction of power and the power connections to slot 0. There are two. One going into connection point 1.1 and another going into connection point 1.2 on the slot 0 card of chassis 1. The red circles on top of the green lines show where the power is coming from. So for sheet on sheet 33, line 10, we have the plus 24 DC voltage coming down from the left side, on the left side of the drawing. On the right side of the drawing, we have 0 volt coming from sheet 23, line 20. If I was to hook up a multimeter to chassis 1, slot 0 at connection point 1.1 and 1.2, I would expect them to read 24 volts. If I was to put a multimeter up to connection point 1.3, I would expect to see 0 volts or ground or common. Under 3310, we see that the wire number is 5051. It's carrying 24 DC volts. It is a 16 gauge wire and is predominantly blue wire with an orange tracer. For the ground line, we see that it is wire number 5033A, carries 0 volts DC, is also a 16 gauge wire and is predominantly white with an orange tracer. Wire numbers, just like device tags, also have meaning. The last number of a wire number is how many devices are connected in series from the power generator. So to the right, we see that we have a power distribution block, which is the main source of power for the circuit shown. This would be the power generation point for the circuit example. The second to the last number and the third from the last number indicate line numbers. So an 04 indicates that it is on line 4. Followed by a 0 means that there are no devices connected in serial. Followed by a 1 means that there's one device connected in serial. And then followed by a 2, so on and so forth. The remaining numbers indicate the sheet number. So after I've taken off the last number for the serial devices, I've taken off the second to the last and the third to the last digits for the the line number. I then get the remaining numbers left for the sheet number. So in this case, it would be on sheet 2, line 4, and have 0 connecting devices in serial before the power generator. Wire number 2041 is going to have 1 device in series, and the power generator is going to be located on sheet 2, line 4. In this case, the power distribution block. We see this little SC that's noted with a round circle in the middle of the electrical circuit. That's a terminal point found in one of the major components, in this case the SCC. Those are not counted as devices connected in serial, and so they don't rev the wire number as it passes through the terminal. Only as it passes through something like a switch, a contact relay, a circuit breaker, things of those nature, will the wire number increase by 1. So now let's trace the power. What we're going to do in this exercise is trace the power line through the electrical prints package. How to trace the power is important for debugging power supplies in the field. If a field device fails, it's one of usually 3 things. Either the power supply to the device is not working, the ground is not returning the power correctly, or the common's not returning the power correctly, or the signal is not being sent properly. All 3 of those actions will require you to trace the electrical circuit through the electrical prints package. What we're about to go through is the same steps that you'll need to go through for debugging most electrical issues, either with the power, the signal, or the ground or common line. So if we look at the drawing on the right, we can see that the wire number 5051 indicates that the power generator is on sheet 5 and line 5, and that there is 1 device connected in serial. But if a problem exists delivering power, then it could be anywhere in the system. The bad connection could be halfway through the circuit or 3/4 of the way through the circuit. We can't just skip to the power generator and say, well, if the power generator is okay, then everything else is okay. In this instance, we know there's at least one device connected in serial, and there are probably some terminal points connected and used along the way that could have a loose connection. The electrical prints package will tell us where those connection points are. So we see that the 24 volt power is coming from sheet 33, line 10 to sheet 34, line 00. Sheet 33, line 10 shows wire number 5051 traveling to sheet 34, line 0, which is correct. That's what we expect. Sheet 33 that we're on, line 4, also shows a terminal point and the power splitting off to supply the 24 volt DC power to connection point 1.2 between slots 2 and 3. This is a possible connection point that could be poorly terminated. Maybe there's a loose connection at this terminal, and that's an area that needs to be checked if you have power supply issues. If that checks out okay, then the drawing shows that wire 5051 now comes from sheet 23, line 20, and goes to sheet 33, line 0. Here we see on sheet 23, line 20, that the 24 volt power is going to sheet 33, line 0, as we expect. We can also see that there are 3 termination points, or terminal points, that the signal splits off to feed other devices. These are connection points that could possibly be poorly terminated. These are issues where if you are having power supply, or these are areas that if you are having power supply issues, the power supply issue could be coming from these terminal points. And if we continue to follow wire 5051, we see that it goes from, or is supplied from sheet 22, line 2 to sheet 23, line 00. And on sheet 22, line 2, we see that feeding sheet 23, line 0. There's a terminal point in the SAC, and then this is traveling, this box here with the note denotes that the power is from the power distribution panel in a different drawing package. So everything inside of this box is going to be inside of this drawing. Because sheet 22 at this note has a black triangle that we see circled in blue, we know that it comes from sheet 5, line 5 of this specific drawing package. So when we go to the PDP drawing package at sheet 5, line 5, we see that that in fact does go to sheet 22, line 2, and is inside of the 121 package that we were looking at earlier. We see that the wire coming to the SAC is actually a 14 gauge wire and is blue with an orange tracer. We also see 505CB device, which is a circuit breaker located on sheet 5, line 5, and we can see that it is a 10 amp circuit breaker. Now this power distribution block is connected to the 24 volt power supply, and we've now effectively traced the 24 volt power supply through the system. The circuit breaker specifically is what takes the wire number from 5050 to 5051. That's supplied to the SAC and eventually to slot 0 of chassis 1. If we're having problems with the power supply to the 24 volt power supply, then we could trace the power back all the way to the transformer, and we would start by looking at sheet 4, line 31. That supplies power to the 24 volt power supply. And eventually we would trace our way all the way back to the transformer where the ultimate power supply is brought into the system. Tracing any electrical signal is the same as the last exercise. Like we talked about right before we jumped into the exercise. Tracing a power supply, tracing a signal malfunctioning, or tracing a ground or common wire or shield wire malfunctioning all follow the same basic steps that we just went through. You can figure out the origination device, the destination device, and all of those in the middle, and figure out where your connection points are by looking at the electrical prints package. This package will have all of that information for you. If you have a pressure regulator that's not receiving a signal, then the signal can be traced the same way as the last example. The way that you do that is examine the devices connected in series to discover the root cause. If you have a pressure sensor that is not feeding back a signal, the signal can be traced from its origin to the destination the same way as the last example. Examine the devices connected in series to discover the root cause. And so if you're troubleshooting with the electrical prints package, the main rule that you're going to follow is examine the devices connected in series to discover the root cause. Now, you may find that it's the first device that's not generating the correct signal, or you may find that it's the last device that's not receiving the correct signal, and maybe those devices need to be replaced. But you figure that out by examining the devices connected in series to discover the root cause. One of the last items that is included in an electrical prints package is the bill of materials. Now, the bill of materials is important for when you're replacing components, specifically listing out or calling out trouble components when describing an issue. The bill of materials lists the components called out on the layout diagram. Now, we looked back at the layout diagram and we saw, for example, that we have this Ethernet switch located on the right, and it's labeled with a bubble 171. Now, if we go to the BOM, we can see that under detail 171, which is what this indicates on the layout diagram, that there's only one quantity of them. The manufacturer is Hirschman, and its description is an 8-port Ethernet switch, which is exactly what we see located on the layout diagram. Each bubble on the layout diagram has a corresponding line item in the BOM. The BOM gives the quantity, the manufacturer, the description, and even the manufacturer part number so that the item can be readily reordered if in fact it fails. One of the last components that we see in the electrical prints package are spare sheets. Spare sheets are used to leave room for expansion. As we talked about, wire numbers and device tags are based on sheet and line number from the electrical prints package. So if I want to add a junction box, I want to add that in an area that all the other junction box wiring is located. I don't want to have to add it to the end of the package and make my package confusing to navigate. So what happens is I'll include a spare sheet, and that way when a junction box is a new junction box is integrated into the system, I can use one of the spare sheets because that allows me to include my device and incorporate it into the overall package without having to rename the later devices and wires. And it'll still be located where my other junction box wiring is. And so that's the point of the spare sheets. When we look at electrical prints, we see common electrical devices located inside of those prints. These are the devices and the internal circuitry of those devices that allow these systems to communicate and drive power correctly. For power and connection and disconnection, we see transformers. Transformers alter the voltage and current per the system requirements. They're generally what we're going to use to deliver the system voltage that we need. We also have disconnect switch, which will interrupt power or disconnect power to the system. And the DC power supply, which will convert AC current into DC current for DC devices. We also see relays. Relays are an electrically operated switch. Relays are used where it's necessary to control a circuit by a separate low power signal. or where several circuits must be controlled by one signal. Relays control one electrical circuit by opening and closing contacts in another electrical circuit. And there are control relays, contactors. Contactors are also an electrically operated switch, but it's a type of relay that can handle the high power required to directly control a motor. We also have safety relays. Safety relays are smart devices that use a minimum of 2 redundant circuits. The redundant circuits must make the same connection within a set time frame in order for the relay to allow a reset condition to occur. If it's not met by both channels in that time frame, the system will stay de-energized. Usually this is used with safety devices like the light curtains, e-stops, door entry switches, things like that. And then we also have the relay coil, which is the internal mechanism of the relay device. I apply power to the coil and I can get an output signal on my contactor. For relays, we have normally open relays. These are relays that when no power is applied, the electrical connection is open and not letting power through. We also have normally closed contacts, and those are when no power is applied, the electrical circuit is complete and power is allowed to flow. There are fuses. Fuses limit the current or amperage through a circuit when it's in an unsafe level. Fuses typically protect electronics and sensitive equipment because they blow faster than circuit breakers. Fuses are one-time use devices. When a fuse does blow, it must be replaced. Circuit breakers limit the current and amperage through a circuit when it's in an unsafe level also, but circuit breakers are designed to protect wiring, circuits, motors, and other more rugged electronics as they blow more slowly than the sensitive electrical equipment. Circuit breakers can also be reset rather than having to be replaced like a fuse. Limit switches are mechanical position sensors. Devices must make contact with an actuator and to physically close the switch. The device has internal contacts used to pass the current through depending on their state. There's also a proximity switch. While a limit switch has to make precise contact to close the system, a prox switch would allow for close proximity to close the switch instead of needing the physical connection. We also have the photo eye type sensor. For the photo eye, you have the through beam type, which will be a sender and a separate receiver. So the sender will send a single beam, the receiver will receive it, and as long as the receiver receives every single beam, then the connection is made. You also have diffuse type, which are sender receiver in the same unit. The target would actually reflect the sending signal and reflect that back into the receiver. You also have a pressure switch, which would use a pressure mechanism to actuate a switch as opposed to a physical pushing connection like we would see in the limit switch or door detect switch. This would require a certain amount of pressure to close the electrical switch. We also have solenoids. Solenoids are electrical devices that convert electrical energy into a linear mechanical force. Generally, the way that standard automation uses solenoids is that it converts an electrical signal into an air signal, and we use that air signal to pilot valves. And so our solenoids convert the electrical signal into the mechanical air signal. We also have intrinsically safe barriers. Intrinsically safe barriers are electrical components which contain internal circuitry designed to limit the energy available to the protected circuit in the hazardous location under the specified fault conditions. So in a painting environment, there are certain current and voltage limitations allowed in that environment to keep it explosion proof. And if a device is rated for more than that voltage and current, then it's got to pass through an ISB, or intrinsically safe barrier, to make sure that the energy going out to the device is limited and stays within specification. And that's all we have for electrical print basics and common electrical components. Thank you very much for your time.